Okay, so we're continuing with our 6.2 notes. So we're on the page that has complete graphs at the top. So a complete graph is going to be a simple graph. So just as a reminder, a simple graph has no loops or multiple edges. So in a complete graph, every vertex is connected to every other vertex by a single edge. A complete graph is denoted K sub n, where n is the number of vertices. So the idea behind a complete graph is if we're thinking about number of sites, like for traveling salesperson problems, we're assuming there's a way to get from any one site to any other. So let's just say we have three vertices or three sites. So we're assuming that from any site we can go to any other. So we get a single edge connecting each one. So this would be K3. Now if we move up to K4, let's say we do kind of a square. Okay, if we start with this one on the left, it will connect a single edge to every other vertex. So we've got three there. This one will also connect. It already goes to the one on the left, so we can go down or across. And then if we draw this one down here, you'll notice that every vertex has three edges coming off of it, so it goes to every other vertex. So that would be K4. All right, so let's look at K5. So drawing 5 vertices, we want to connect a single edge to each vertex. So you just kind of pick a starting point and then you work your way around. So once I'm here, I've already gone to that top one, so I'm going to go across, down, across here. All right, when I get to this one, I can go straight across, straight over to this one. And as you move around, you'll draw less and less edges because some of them are already drawn for you. All right, so that would be K5. And let's try K6. We'll make this the last one. All right, so I'm going to try to spread these out a little bit. All right, so we've got 6 vertices. We're going to connect. This would look prettier if I used a ruler, but in graph theory, it doesn't really matter if your lines are straight anyway. So we connect to each and every vertex once. So we go there. And then each time you draw, you get one less than the time before. So 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Now if you spread these out, this kind of makes a pretty design if you evenly space them. I just kind of hand drew it, so not the best in the world. All right, so some things that are true about complete graphs. The degree of every vertex in K sub n is n minus 1. And we can see an example of that. For example, in K5, we count 1, 2, 3, 4 lines because it's got to go to the other 4 vertices. So it's always going to be one less than the number of vertices. Now the number of edges, this is a little bit harder to remember. It's n times n minus 1 over 2, where n is your number of vertices. Then we have the number of Hamilton paths. So just as a reminder, a Hamilton path visits every vertex once and only once. And this is going to be n factorial. So if you haven't seen the factorial before, just to kind of show you an example, if you're given 5 factorial, that means 5 times 4 times 3 times 2 times 1. And let's see if we put that in our calculator. Clear that out. 5 times 4 times 3 times 2 times 1. We get 120. So for that graph K5 that I drew, it would have 120 different Hamilton paths. If we did something like 8 factorial, that'd be 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. So it starts with that number and it just goes down. So you can see these get really big really fast. So 8, 7, 6, 5, 4, 3, 2, 1. if you had K8, it would have 40,320 Hamilton paths. So you wouldn't want to have to write all those down. Now Hamilton circuits, there's not quite as many of those. So for that one, we use n minus 1 factorial. Notice the n minus 1 is in parentheses. So however many vertices we have, we take one off of that, and then we take the factorial. All right, so let's answer some questions here. We have how many edges are in K20 and K21. So in K20, we know that n equals 20. So we go up and get our formula for number of edges. N times n minus 1 over 2. And everywhere we have an n, we're going to put a 20. So 20 times 20 minus 1 over 2. If we follow our order of operations, do our parentheses first. That's 20 times 19 divided by 2. Okay, so 20 times 19 divided by 2, that gives us 190. So we have 190 edges in the complete graph that has 20 vertices. So if we just bump it up to 21, we just add one more vertex. We're still doing number of edges, so n times n minus 1 over 2. But this time everywhere we have an n, we're putting a 21. So we end up with 21 times 20 divided by 2. And if you work that out in your calculator, it turns out to be 210 edges. So just by adding a single vertex, you can see we added 20 more edges there. All right, so here's a few more. We have how many Hamilton paths are in K10. So you have to get the right formula. Hamilton paths is n factorial. So that would be 10, since we're doing K10. 10 factorial is 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. Now some calculators have a factorial button, but it is kind of hard to find, so you can always just type it in. 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. And the answer is a whole bunch. It comes out 3,628,800. So that is a whole lot of Hamilton paths. 3,628,800. Okay, Hamilton circuits. This time we're looking at K8, so n is 8. So for Hamilton circuits, remember the formula is n minus 1 factorial. So remember n is 8, so 8 minus 1 factorial. You do your parentheses first. That's going to be 7 factorial, which is 7 times 6 times 5 times 4 times 3 times 2 times 1. So if I stick that in my calculator real quick, that comes out to be 5,040 Hamilton circuits. So you can see it doesn't take very many sites or very many vertices to make a whole bunch of Hamilton circuits and Hamilton paths. All right, our last one is the degree of every vertex in K18. So on this one, n is 18. Degree is easy. It's just n minus 1. So that'll be 18 minus 1. So the degree of each vertex would be 17. All right, now on the next page we have example 5, and we're actually going to skip that one for now. So we'll take this one out, skip over that. And I do want to take a few minutes to talk about weighted graphs. In traveling salesperson problems, you have a weight. Sometimes it's a distance or a time. So this, for example, could be the amount of time it takes to drive from point A to point D. So notice this is not to scale, so A to C would be 15, C to B would be 21. So if you want to think about it as time, you can do that, or maybe how much it costs you in gas or something like that. All right, so we're asked to find a Hamilton circuit that ends with edge BD. So notice we're going to end by going from B to D. So remember, on a circuit we have to start and end at the same place. So if we're going to end at D, we know we have to start at D. So we know that. And remember, for a Hamilton, we have to visit each vertex once and only once. So from D, I can either go to A or go to C. I don't want to go to B because I know I have to end with that. So the problem is if I go D to C, I don't want to do B yet because I want to save it for last. If I come up to A, I don't have a way to get to B. So D to C is not a good idea. So let's try D to A. So we'll go D to A, then we'll go to C, then we'll go to B, and then we go back home to D. All right, so there's our circuit. Now let's do the weight. So from D to A, it was 5. Then we went from A to C, which was 15. Then we went C to B, which was 21. And then B back to D was 7. So if we add those together, we do get a total of 48. So if you're thinking about time, maybe that's 48 minutes. Maybe it's $48 in gas. We don't know what the weight is. All right, so here we want to find a Hamilton path that starts at A and ends at B, and we want to give its weight. So we have to go through every vertex once, start at A and end at B. There are a couple of options. We could go kind of counterclockwise. We could go A, D, C, B, right? That gets every vertex once. So A to D would be 5, D to C would be 10, C to B would be 21, and that would give us a total weight of 36. Now somebody else may have gone a different way. They may have said, okay, instead of going to D first, I want to go to C. So they may have gone A to C, then D, then B. Okay, so both start at A and end at B, so they meet our qualifications. So A to C would be 15, C to D would be 10, D to B would be 7, and this one turns out to have a weight of 32. So if you're thinking time, maybe going this route saves you 4 minutes, and maybe that's the route that you want to take. All right, let's look at this last example. So we're given a Hamilton circuit in a graph. We're not given the picture, but we know we went to every single vertex once, and then we started and ended at A. So what we want to do is write 2 Hamilton circuits using E. So what we're going to do here is we're going to use the answer we already have, and we're going to keep the order the same. Okay, so I'm going to take this list that I have, and I am going to start with letter E, and then I'm going to read it going this direction. So I'm going to go E, F, A, and then once you get to A, you're going to go back to the beginning. You're not going to write A again, but you're going to go B, C, D, and remember it's a circuit, so it has to start and end at E. All right, so now I'm going to do the same thing. I'm going to start at E, but this time I'm going to go left. So I'm going to have E, D, C, B, A. Once I get to A, I go back to the end, and I'm still going to the left. I do not write the A twice. I'm going to go F and then back to E. Okay, so this is a way to get more circuits out of a circuit that you already have. All right, now if I want to do paths that start at E, remember a path doesn't go back to the beginning, so you're going to take your answer from A and you're just going to remove the last edge. Okay, so if I bring this answer down, it'll be E, F, A, B, C, D. I'm not going to travel that last edge back to where I started, so I'm just going to remove the E. Same thing here, E, D, C, B, A, F. Okay, so I just took the E off, and now I have a path instead of a circuit.